National Electrical Code Section 220.41 permits a diversity allowance of 35% for fixed electric heating equipment rated over 10 kilowatts. It is important to know that this allowance does not apply to electric heating equipment installed in bathrooms, kitchens, or other rooms where the load diversity is not expected. The allowance also does not apply to heating equipment specifically designed to be operated continuously. To determine the connected load for the heating equipment after applying the diversity allowance, use the following formula: connected load equals rated load times diversity allowance. For example, if there is a fixed electric heater with a rated load of 15 kilowatts, the connected load for sizing the electrical service would be connected load equals 15 kilowatts times 0.35, which equals 5.25 kilowatts. The diversity allowance is typically only applied to the heating elements of the equipment, not to any associated motors, fans, or controls. The actual diversity factor may vary depending on the specific application and usage patterns. It is always important to consult with local electrical codes and authorities to ensure compliance. When calculating electrical loads, it's crucial to differentiate between demand factors and diversity factors, as these terms are often used interchangeably but represent distinct concepts in electrical engineering. Demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system, or part of the system, under consideration. This factor is applied to estimate the likely maximum load that a system will draw at any given time, considering that not all connected loads will operate simultaneously at their full rating. The formula for demand factor is demand factor equals maximum demand divided by total connected load. For instance, if a building has a total connected load of 100 kilowatts, but the maximum demand recorded over a period is 70 kilowatts, the demand factor would be 70 kilowatts divided by 100 kilowatts, which equals 0.7. This indicates that on average, the system is only using 70% of its total connected load at any given time. Demand factors are typically used for sizing electrical services, feeders, and transformers to ensure that they can handle the expected load without being oversized, leading to unnecessary costs. They are often based on historical data, statistical analysis, or empirical studies of similar installations. Diversity factor, on the other hand, is the ratio of the sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the complete system. It accounts for the fact that the peak demands of different loads within a system may occur at different times. The formula for diversity factor is diversity factor equals sum of individual maximum demands divided by maximum demand of the entire system. For example, consider a hotel with several electric heating units. If the sum of the maximum demands of each individual heating unit is 50 kilowatts, but the maximum demand of the entire hotel's heating system at any one time is 40 kilowatts, the diversity factor would be 50 kilowatts divided by 40 kilowatts, which equals 1.25. This indicates that the system's overall maximum demand is less than the sum of the individual maximum demands, due to the likelihood that not all heating units will be operating at their peak simultaneously. Diversity factors are used to optimize the design of electrical systems by allowing for a reduction in the size of equipment and conductors based on the understanding that peak loads are not concurrent. The key difference between demand factors and diversity factors lies in their application and perspective. Demand factors are applied to estimate the maximum demand of a system relative to its total connected load, while diversity factors are used to determine how the maximum demand of an entire system relates to the sum of the maximum demands of its individual components. Demand factors are typically less than 1, reducing the calculated load, while diversity factors are typically greater than 1, also reducing the calculated load by recognizing non-coincident peak demands. It's important to note that while the National Electrical Code, or NEC, provides guidance on demand factors for various types of loads, diversity factors often require engineering judgment and may vary based on specific application and historical data. In the context of sizing electrical services for a hotel with fixed electric heating equipment, the NEC 220.41 allows for a diversity allowance of 35% for fixed electric heating equipment rated over 10 kilowatts, which can be applied to reduce the calculated load for service sizing. However, this allowance is subject to certain exceptions, such as heating equipment installed in bathrooms, kitchens, or other areas where load diversity is not expected, as well as equipment designed for continuous operation. Additionally, it's important to consider that the diversity allowance typically applies only to the heating element and not to any associated motors, fans, or controls. Therefore, a comprehensive load calculation should include all relevant loads and applicable demand and diversity factors to accurately determine the required electrical service capacity for the hotel. In addition to the NEC guidelines and the distinction between demand and diversity factors, several other crucial considerations come into play when sizing electrical services for a hotel with fixed electric heating equipment. These considerations ensure the safety, reliability, and efficiency of the electrical system. Firstly, conduct a thorough load analysis. A detailed load analysis is essential to identify all electrical loads within the hotel, including lighting, receptacles, HVAC systems, elevators, kitchen equipment, and any other significant electrical consumers. This analysis should categorize loads as either continuous or non-continuous, as well as determine their demand characteristics and operating schedules. Accurate load data forms the foundation for subsequent calculations and decisions. Secondly, consider future expansion. When sizing electrical services, it's important to account for potential future expansion or increased electrical demand within the hotel. This may involve adding spare capacity to the service equipment, feeders, and distribution panels to accommodate anticipated growth or new loads. Overlooking future expansion can lead to costly upgrades or modifications down the line. Thirdly, evaluate voltage drop. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can impair the performance of electrical equipment, reduce energy efficiency, and potentially damage sensitive electronics. It's crucial to calculate voltage drop for all branch circuits, feeders, and service conductors to ensure that voltage levels remain within acceptable limits. The NEC provides guidelines and formulas for calculating voltage drop, and appropriate conductor sizes should be selected to minimize voltage drop. Fourthly, think about short-circuit protection. Adequate short-circuit protection is essential to protect electrical equipment and conductors from damage in the event of a fault or short circuit. Short-circuit protective devices, such as circuit breakers and fuses, must be selected and coordinated to interrupt fault currents quickly and safely. The selection of these devices should be based on the available fault current at various points within the electrical system, as well as the withstand ratings of the equipment being protected. The NEC provides requirements for short-circuit protection and coordination studies. Fifthly, ground fault protection should be analyzed. Ground fault protection is designed to detect and interrupt ground faults, which are unintentional electrical connections between a phase conductor and ground. Ground faults can pose a significant shock hazard and may also cause fires or equipment damage. Ground fault protection is typically required for service disconnects and feeders serving certain types of loads, such as those in healthcare facilities or industrial plants. The NEC specifies the requirements for ground fault protection and the types of equipment that must be protected. Sixthly, coordination and selective tripping are important. Coordination and selective tripping refer to the practice of coordinating the operation of multiple overcurrent protective devices to ensure that only the device closest to the fault opens, minimizing the extent of the outage. Selective tripping is essential for maintaining system reliability and preventing unnecessary downtime. Coordination studies should be conducted to verify that overcurrent protective devices are properly coordinated and that selective tripping is achieved. Seventhly, consider power quality. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, harmonic distortion, and transient disturbances. Poor power quality can adversely affect the performance of sensitive electronic equipment, cause equipment malfunctions, and increase energy consumption. Power quality issues may be addressed through the use of power conditioning equipment, such as surge suppressors, harmonic filters, and voltage regulators. Eighthly, energy efficiency should be addressed. Energy efficiency is an increasingly important consideration in the design and operation of electrical systems. Energy-efficient equipment, lighting controls, and building automation systems can significantly reduce energy consumption and operating costs. Additionally, demand response programs and energy storage systems may be implemented to optimize energy usage and reduce peak demand charges. Ninthly, adhere to local codes and regulations. In addition to the NEC, local codes and regulations may impose additional requirements or restrictions on the design and installation of electrical systems. It's essential to be familiar with and comply with all applicable codes and regulations to ensure that the electrical system is safe, legal, and meets the needs of the hotel. 10thly, documentation is important. Complete and accurate documentation of the electrical system is essential for future maintenance, troubleshooting, and modifications. This documentation should include single-line diagrams, panel schedules, wiring diagrams, equipment specifications, and any other relevant information. Proper documentation facilitates efficient maintenance and reduces the risk of errors or omissions. By carefully considering these factors and following established engineering practices, it's possible to design and install electrical services for a hotel with fixed electric heating equipment that are safe, reliable, efficient, and compliant with all applicable codes and regulations. The NEC provides specific guidelines for calculating the ampacity of conductors based on their insulation type, temperature rating, and installation conditions. Ampacity refers to the maximum current, in amperes, that a conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The NEC tables 310.15b16 through 310.15b19 provide ampacity ratings for various conductor types and sizes based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit and no more than 3 current carrying conductors in a raceway or cable. When conductors are installed in conditions that differ from these base conditions, ampacity adjustment or correction factors must be applied. Firstly, the temperature correction factor must be determined. If the ambient temperature exceeds 30 degrees Celsius or 86 degrees Fahrenheit, a temperature correction factor must be applied to reduce the allowable ampacity of the conductor. The NEC tables 310.15b16 through 310.15b19 provide temperature correction factors for various conductor insulation types and ambient temperatures. For example, if a conductor with a temperature rating of 75 degrees Celsius is installed in an ambient temperature of 40 degrees Celsius, a temperature correction factor of 0.88 may be applied. Secondly, the adjustment factor for the number of conductors must be determined. When more than 3 current carrying conductors are installed in a raceway or cable, an adjustment factor must be applied to reduce the allowable ampacity of the conductors to account for the increased heat generated by the conductors. The NEC table 310.15b3 provides adjustment factors for various numbers of current carrying conductors. For example, if 7 to 9 current carrying conductors are installed in a raceway, an adjustment factor of 0.70 must be applied. Thirdly, calculate the adjusted ampacity. To calculate the adjusted ampacity of a conductor, multiply the ampacity rating from the NEC table 310.15b16 through 310.15b19 by the temperature correction factor and the adjustment factor for the number of conductors. For example, if a number 12 American wire gauge or copper conductor with a temperature rating of 75 degrees Celsius has an ampacity rating of 30 amps and is installed in an ambient temperature of 40 degrees Celsius with 7 to 9 current carrying conductors in a raceway, the adjusted ampacity would be 30 amps times 0.88 times 0.70, which equals 18.48 amps. Fourthly, consider other factors that impact the adjustment. In addition to temperature and the number of conductors, other factors may also affect the ampacity of conductors, such as the presence of harmonics, the type of load served, and the conductor's operating environment. These factors should be carefully considered when determining the appropriate ampacity for a conductor. Fifthly, select the appropriate conductor size. Once the adjusted ampacity has been calculated, the appropriate conductor size can be selected based on the load requirements and the NEC ampacity tables. It's important to select a conductor size that is large enough to carry the load current without exceeding its temperature rating, while also considering factors such as voltage drop and short circuit protection. Sixthly, follow the NEC guidelines. The NEC provides detailed guidelines for calculating conductor ampacity and selecting appropriate conductor sizes. It's important to be familiar with these guidelines and to follow them carefully to ensure that electrical installations are safe and compliant with code requirements. In addition to these considerations, it's also important to consider the conductor's insulation type, which affects its temperature rating and ampacity. Common conductor insulation types include THHN, THWN, THW, and XHHW, each with different temperature ratings and applications. The NEC specifies the allowable uses for each insulation type and provides ampacity ratings based on the conductor's temperature rating. When selecting conductors for a specific application, it's important to consider the ambient temperature, the number of conductors in a raceway or cable, and any other factors that may affect the conductor's ampacity. By carefully following the NEC guidelines and considering all relevant factors, it's possible to select conductors that are appropriately sized and rated for the intended application, ensuring the safety and reliability of the electrical system. Understanding how to accurately size conductors, apply ampacity correction and adjustment factors, and account for various environmental conditions is crucial for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. Proper conductor sizing ensures that electrical systems operate safely, efficiently, and reliably, while also complying with applicable codes and regulations.